You guys know where you can find my live stream thing? It's actually under announcements on the first page. If you look there, you can find it. Someone from my other class asked about it because you might want to do the live stream if you're going to be late to class or whatever, and you don't want to do the Zoom. Just listen to the live stream. All right. Switch over to your class. Okay. I want to do the live stream if you're going to be late to class or whatever. I'm closing the live stream because if I leave it on, it's messy. All right. Okay, so mod 5 will be opening up soon. And in mod 5, you will find the test at the end because it will not open up, actually won't show up until Friday. You guys could take it Friday, right?
What quiz?
No, the test. Friday morning, early. No, next Friday. Tomorrow is this Friday. Next week.
What time?
Anytime between midnight, Thursday night, and midnight, Friday night.
Oh,
I can probably try like in the morning, cause like I'm working 2 out of 10.
Good. So 10. So 10 to 11 or it probably won't take you much longer than an hour to do.
Yeah, but 10 like I come home at 10.
Then 9. No, 10 in the morning.
Yeah, I'm saying in the morning, probably take it in the morning.
Yeah, 10 in the morning. You have an hour. Still have time to get ready. Take it earlier if you want. It shouldn't take you much more than an hour. And it probably won't even take an hour. But, okay. What do you want to know about that test? Anything we need to know about that test? Oh, this is homework 5. We're not doing homework 5.
Do you recommend having like pen and pad to work out problems or anything?
I recommend that you not have those things.
Okay.
Here's my feeling about that, about tests anymore lately. They are, I want you to think of them as an interview. Okay. In other words, you're going to be asked questions. You're going to be asked questions and you're going to answer them. But the bulk of the questions, look, the first questions are vocabulary questions. What is math? What is calculus? I don't know which ones you're going to get. They're kind of random. But I've asked if you saw them as choices on the quizzes, like the quiz about multiple choice, these are not going to be multiple. You're just going to have to answer them. Just got to say them out loud. Okay. Do the best you can to answer those questions. So the first 3 questions are saying out loud the vocabulary. The next 3 questions are read limits and derivatives. Just going to read them. So they're also saying out loud. So there's nothing to write for any of those. The next group of 3 questions is going to be what happened here. So for questions like the product rule or the quotient rule or something where I don't really want to give you a hard problem, I'll ask you, I'll show you a homework question and say what happened here. And you'll say, well, it was a product rule or a quotient rule. But those are multiple choice, but not to actually pick all that apply. So that makes them a little harder. So you have to, if it was a product rule and a chain rule, you have to say both of them. The next 3 questions are solve things. You know, solve this, solve that. And those are just regular math questions, but there's only 3. Of the 15 questions, 3 of them are actually where you might want to use a piece of paper and a pencil. Okay, and I ask that you use Desmos instead of using a piece of paper and a pencil. So write everything you can on Desmos. If it's a problem that requires a picture or whatever, I don't usually put them on the exams because Desmos sucks at pictures. Like if you needed a piece of paper to draw something like a picture of of a lake or something, I wouldn't ask that question usually. Okay. So I
Okay.
only, so yeah, so don't, and again, it's like an interview. Because if you start writing stuff on a piece of paper and whatever, it's really hard for me to know what's going on. Like I don't know what you're doing. And it's I would rather you just try to answer the questions as best you can. If you're doing work on Desmos, I can see you're doing work on Desmos. It's like you're answering the question. But if you write stuff or use a calculator, or whatever, I don't know what's going on. So no. So the answer is don't do that. And see, try it for this test. If it's a problem, talk to me afterwards. But most people in this course figure out that Desmos is the best friend you have. And it really is a much easier thing than, it's an easier tool to deal with than note paper or calculator or anything. Okay. The last three questions are going to be, it's from data. You get data, you're going to have to answer a question. And what have we done so far? We've done average rate of change in the discussion. We've done instantaneous rate of changes, and we've done I don't think mean value theorem isn't due until maybe mean value theorem. That's no, I don't think mean value theorem is still the midterm. Anyway, so those are things you'll see on the test. Okay. I'll talk more about it next week. All right. Any questions from homework 3? You have homework 4 coming up. Okay. Homework 4 is this one. Homework 4. Okay, so there's some of these guys right here. The first 4 of them are examples of implicit differentiation. Then there's going to be a Newton's method, a Newton's method, and a Newton's method, 3 Newton's methods. Then there's an acceleration velocity one, and then there's 2 acceleration velocities. And then there's a compute the 4th derivative. And then there's a hyperbolic trig function derivative. Okay. Let me just say this. For these implicit differentiations, I'm contractually obliged to give you difficult problems or some difficult problems. But as far as the test goes, I generally stick to question number 1. Or I do question number, or maybe question number 4. Bless you. But I won't, question 2 and 3 are just difficult to do. I wouldn't count on them. At best, you'll see them in a what happened here question. Newton's method. I love Newton's method. It's a great method, but I have to stick with the times, and it's not useful anymore. I mean, it helped explain how computers, like if you had something like you wanted to solve an equation, like this equals x, like if you want to solve that equation, you're actually solving this equation, x cubed equals 11, which means you're also solving this equation, x cubed minus 11 equals 0, which means you can create a function. You could create a function that equals x cubed minus 11, and you could find the 0 for that. And if you find the 0 for that, then you find the answer. So the answer would be somewhere around here. It's this way. So it's like 2.22. Okay. So that's what, so we set up this function, and then we use this algorithm that processes it, that does a guess. We start with a guess, and then we that guess gets tried again and again and put into Newton's method. I think I want to show you something. The formula, this is the formula sheet. You see the first one on the formula sheet is the Newton's method formula. Okay. These formulas you're allowed to have at any time. Okay. All right. Where was that? Here. All right, so Newton's method, if I ask you to use Newton's method, you have to use it. So even if you can get the answer, one way to get the answer, by the way, is this is what some people do, but you can't do it this way. You can zoom in. So to see the answer is 2 point. See how I'm zooming in right there? It's 2.22398. If I just keep zooming in.
Yeah, you should put this, you should share the screen.
Oh, thank you. I'm not sharing the screen. Am I sharing the screen now?
What is the answer to the, can you go up a second?
I am sharing the screen. Yes, it says I'm sharing the screen.
Yeah.
But you see what I'm doing? I'm zooming in. If I want 6 decimal places, I can just zoom in and I can count these boxes. 2.2398. Gosh, I don't even know how I can do any more in here, but some people try to zoom in that way. That's not an acceptable way of using Newton's method. If you're going to use Newton's method, you have to go to the formula sheet. Here's the formula sheet. Here's the formula sheet. You can get this right here. Copy it and paste it. Okay. Okay, so you could create a function. You can do that. You can guess that the answer is 2.22398. 2.22398. So you can take that, copy, put it here. Okay, this isn't working because the function has to do something I know. Okay, so there's the answer, 2.22398. 00905. So I would say that's not changing, and so that's probably good enough. So I just use Newton's method once. If I use it again, I should get a number that's equally close. In other words, if I take this number and plug it in there, take this number, copy it, and put it in here. Okay, so you see the number hasn't changed. That's the answer. 2.239800957. Okay. If I say use Newton's method, you have to use Newton's method, even if it's this problem as simple as the cube. By the way, the cube root of 11 is that 2.22398000757. So it's the same answer. Okay. Back to my. All right. So last time you did the work on derivatives, right? Next time is when the trans is due. So today, trans means transcendental functions. So today, if we break up into our groups later on, we're going to be moving on to the next one, the mean value theorem. That isn't going to be due for another week or so. But if we get it done early, then that's one less thing for us to worry about. Okay. All right. Class questions. Let's go over the class questions and see how much we remember from. Oh, you know what? Let me wait. Last time we did implicit differentiation, hyperbolics, Newton's method. Okay, and then now I have to do higher order derivatives. That's what I'm going to do today. Okay. All right. So let me review. I'll do that in a second, but so for review, we did the definition. So Some people have been asking me, like, they're just not sure what a derivative is. What is a derivative? What is the derivative? Who's going to get this question anyway? I might as well look it up. Someone's going to get this question. I'll just ask you right now. Okay, Luke. Is Luke here?
Yeah, I'm here.
Hey, Luke. Can you answer your question out of place here? What is another way of saying the IRC?
The slope of the tangent line or
Slope-
velocity.
Velocity. Okay. IRC means instantaneous rate of change. Derivative, dy dx. Yes, also on that list, Luke. The derivative. So the slope of the tangent line is the derivative. The derivative is these things. They're all the same thing. Instantaneous rate of change. It's the derivative. Slope of the tangent line, derivative. So what is the derivative? It's the slope of the tangent line. Okay, let me look it back to. All right. So the definition of this this slope of the tangent line, or the definition of derivative, was this thing right here. We had the function. That's the definition of derivative right there for f. When the students ask me another question, well, what's the derivative of, how do they know what the derivative of cosine is? Well, because they do this, they plug cosine in. Oops. I guess not. They replace these f's with cosine, and they solve that problem. And they use some trig identity. Remember the cosine of a plus h is the cosine a, cosine h minus sine a, sine h. Remember that? Maybe you don't remember it, but that was it. So you do all of this stuff, you find it, and you find some limits, and you plug them in, some of them go to 0, and blah, blah, it all boils down to sine. If you want to see that proof somewhere, you can see it somewhere. But once it's done, you don't have to remember it again. So the derivative of sine is cosine, derivative of cosine is sine. Okay? And we have all these different notations. You could also evaluate them at a value like a, or you could just have it as generic function. You could have f prime of x. These right here are just generic derivatives. In other words, the derivatives can be represented as a function. You tell me what you're interested in, and I'll tell you it is by using the function. Okay? I'm not going to ask you to do the definition of derivative. I'm contractually obliged to show it to you and to tell you that it's used and we will use it, but you probably won't have to do anything with it. Okay? Because you have better things to do. You have quick and dirty rules to do. But anyway, if you want the equation of the tangent line, if you want the equation of a line, you need a point and a slope. So what you're going to need, if you need the equation of a tangent line, is you're going to need the point on the curve, which you can get by just plugging a in. So a is, you plug in a for x, and then you get f of a. But then if you want the slope of the tangent line, that's the derivative. Okay? And so that's how you find the equation of a tangent line. All right? And then you have all these quick and dirty rules for finding derivatives. There's the product rule, the power rule, the quotient rule, the chain rule. These are all quick and dirty ways. Right? Then we have derivatives of transcendental functions, derivative of e to the x, derivative of natural log of x, the derivative of log, the derivative of these I added. So I wouldn't, there's formulas for log base 3 of x. But yeah, I don't care. You can find these. You can actually ask the derivative of tangent. I think you can ask Siri for the derivative of tangent and it'll tell you. Okay? All right. The chain rule. That one was when you had a function inside and a function outside. So if you have an inside function, your derivative is going to have the inside function repeated somewhere, and then you're going to have the derivative of that. So you're going to have two things you got to see when using a chain rule. So if you're taking the derivative of f of x to the 4th power, you see the power, you bring the 4 down, and you'll take take one away, and you leave the inside alone, and then you take the derivative of it. Okay? All right, so we use the chain rule quite a bit. So that's one that you really ought to know. All right, velocity and position, velocity, position, acceleration, just derivatives of each other. The mean value theorem we did last time. So this is an application of derivatives. The mean value theorem is simply when you have an average rate of change, and you say, when is that equal to the instantaneous rate of change? Okay, the specific example of that was the police giving you a ticket for speeding on you. If you've done 100 miles in an hour, then you did 100 miles an hour. And at some point you did 100 miles an hour. Okay, you'll get a ticket for doing 100 miles an hour because of the mean value theorem. Can you let him in? Okay. There are other theorems. The squeeze theorem and the intermediate value theorem. The squeeze theorem is used to find limits. In fact, it was used to find the derivative of sine and cosine because they used the theorem because they didn't have decimals at the time. So they use this theorem, but you won't see the squeeze theorem any place in your life. What? Okay. So squeeze theorem, no. Intermediate value theorem. Does anyone know what the intermediate value theorem is? Don't care. Okay. If I do something continuously, if I stare at Sebastian and I'm staring continuously over here. Okay, so if I stare continuously from Sebastian to Slade, there's some intermediate values. You guys here are intermediate values. Do I necessarily have to stare at you? I'm going continuously from Sebastian to Slade. Is there any way I could avoid staring at you? You're in between, right? I have to, so yes, so I have to stare at you at some point if I'm going continuously. If I'm not going continuously, if I close my eyes and go like this, I'm not continuously staring, then sure, I don't have to see you. Okay, so the intermediate value theorem just means that if there's some intermediate value in between, then I must have gone there. So one of the things we'll use it for is if I have positive values of a function and it's positive over here and over there it's negative, and I went continuously from here to there, at some point I passed through zero. There had to be a zero there. So zeros are important, and that's why we use it. But I'll talk to you some more about that particular theorem when we get to curves and stuff. All right. So what was the new material we did last time? Implicit differentiation. I don't remember what. Oh, let me do the what is math stuff first. What is math stuff? There's this. Here we go. Rudra. What? And give me your best answer. So what is your best answer for what is calculus? Calculus?
It's a study of change.
Okay. And math is a language. So calculus is the language that has to do with change. Okay. Sebastian, what is changing? Functions are changing. Okay, good. Pamela, are you here?
Yes.
Okay, Pamela, you get the next question. Which is, I lost it already, hold on. What are the two rates of change?
Average and instantaneous.
Jonathan, how many points do we need for average rate of change?
2.
2. Pavani, how many points do we need? Why did we invent limits?
To take the 2 points of the average rate of change to the 1 point of the instantaneous rate of.
Very good. And Alicia, what do we need for continuity?
The limit
limit used to exist.
The limit exists.
Um, the limit, something, I can't remember the other two.
Sebastian, what did you say was changing? Say that word again. Say that loud enough for her to hear. I'll you something. So the limit exists, and what else exists? Function exists, and what? They have
The
to be.
limit equals the function.
Yes, that's it. Woohoo! See? There you go. Luke, what were the other? You already answered that question. How many points do you need for instantaneous rate of change? You only need 1 point. All right, Slade, what's the derivative of a constant?
0.
0. Acacia, what's the derivative of x to the nth power? Acacia, you're here. I see you.
Sorry. N times x to the minus, n times x to the n minus 1.
Yes, that's the power rule. Cody is not here again. Cody, are you here? I feel like he's not here again. Okay. Eric, what does the quotient rule say? Answer it, and answer it this time. I want to hear it.
The quotient rules the derivative of fx times the g minus this f times the derivative of g all divided by x squared.
G squared, D squared, yes. No x squared, but G squared, yes. Okay, Aiden. What is the derivative of e to the x and the derivative of natural log of x?
The derivative of e to the x is e to the x, and the derivative of natural log of x is 1 over x.
Very good. Selena. What's the derivative of sine, cosine, and tangent? 3 answers.
The derivative of sine is cosine. The derivative of cosine is negative sine, and the derivative of tangent is secant squared.
Very good. Garb, what's the relationship between position, velocity, and acceleration?
So acceleration describes how velocity changes, and velocity describes how position.
And what would we be using in his calculus class to describe that change? Average rate of change? No,
Velocity is your derivative.
it's derivative. Yes, so it's the first derivative, and acceleration is the. Yep, there you go. Because when you say, I'm describing how they change, that's the whole point. What is calculus? Hey, what is calculus, Suja? What are the 2 rates of change?
Sorry?
What are the 2 rates of change that we talked about in this class?
Average rate of change in US.
Right, so we have 2 different types of change. So when you talk about, we want to talk about the change, like acceleration is the change of velocity, you have to be specific. Which one is it? Is it the average or is it the instantaneous? It's the instantaneous. Okay, so the acceleration is the instantaneous rate of change of velocity. Velocity is the instantaneous rate of change of position. And why I hated physics so much is because they actually would talk about the other rate of change. They would say the average velocity or something that is equal to that. So they actually were talking about an average rate of change for velocity, and they would give it some funky name. Okay, but yes, we are talking about change, and with acceleration and velocity are just mentions of that. Okay, all right. Let's see what else. I don't want to do that yet. Where's my mind? Here we go. All right. So what we did this time, we did implicit differentiation. So I want to mention the implicit differentiation. Remember I did that ellipse thing? Remember this? I'm asking you, Sebastian, what did you say calculus was? The study of change. What was changing? Function. So here's a problem with this guy right here. That guy right there, is that a function? Say no. That's not a function. So when we're talking about the average rate of change, we're really, we can find it, not average, instantaneous. We can find the slope of the tangent line, but it's not really of a function. So it's just kind of an ugly thing to do. But we will be doing implicit differentiation to functions. Next time, we're going to be finding the derivatives of inverses, and we're going to need implicit differentiation. But the idea of implicit differentiation is pretty simple. You just take the derivative. You have an equation, you have one equation, one thing here, one thing there, you just take the derivative of both sides. Okay, so I'm going to take the derivative of this, I'm going to take the derivative of that, and set them equal to each other, and then I'm going to solve. Okay. Any questions on that? Implicit, were you guys okay with implicit differentiation that one of the last time? Okay, well, it's going to be on the homework, and I'm going to do it again next time with inverse functions. Okay. Hyperbolic functions. So we talked about these functions, yes? How do you say this? I'll ask this question, which is going to be a question I'm going to ask you next week. How do you say that right there? It's highlighted.
Is that
Go ahead. Go ahead. Eric's going to try to say it, but I'm not going to hear him. Eric, how do you say it?
I think it's sine h of x. Is that how you say that?
Oh, boo. Say, what are you going to say?
I mean hyperbolic cosine.
How about hyperbolic sine? Is that what you were going to say? Say the other.
Yes.
Say the other word. This one.
I mean
Say that out loud.
sine ch.
No, I'm waiting for Slade to say it. He's here. Say it out loud so we can hear it.
Wait, what is that? Hyperbolic is sine.
Well, hyperbolic sine or
Sine CH.
no.
Wait,
How would you say that word?
Finch.
say.
In a cinch. It's not a word. I feel like I've seen that cinch
Yeah.
on Wordle. Yeah, so okay. And now would you say, okay, here's the other one. COSH is said. Say that out loud. Kosh. Cinch and Kosh are the only ones that have names. The rest you have to say hyperbolic tangent, hyperbolic secant, hyperbolic. Do not try to say tan or tan H. Never say H. It's hyperbolic tangent, and that's it. Hyperbolic secant, and that's it. But I just want to tell you this so you don't freak out about this. These are just new functions that you won't see again until Calc 3. I don't think they're mentioned at all in Calc 2. In Calc 3, only thing we need them for is the identity. There is an identity with hyperbolic trig functions, and that is, sine squared plus cosine squared is 1. The identity for this one, and again, I'm not even going to write it down because you don't need to know it until Calc 3, and you won't remember until Calc 3 because I know, because when I taught Calc 3, no one ever remembered this. If you square the hyperbolic cosine and subtract the hyperbolic sine, you get 1. So cosh squared minus sinh squared is 1. That identity we use in Calc 3. All the other stuff we don't use ever. But it's a nice review of notation. If you have it raised to the -1 power, if you have sinh raised to the -1, that doesn't mean 1 over, it means inverse. Okay? So we're going to do inverse functions next time. Okay. Fine. Any questions on hyperbolic? The only thing I'm ever going to ask you in this class is for you to take the derivative of a cosh or a sinh. Nothing else. Nothing. Maybe a cosh will be squared, or maybe it'll be the cosh of 2x or something, but it will never be hyperbolic tangent, hyperbolic cosecant. I shouldn't say never. I think never. Okay. All right. We went over Newton's method, right? That was the one where you tried to find the zeros. I don't need to do that again. If you have some function like this, hold on, let me turn that off. If I have some function and I want to find the zero, I want to find that 0 minus 1.53209. I set up z, and I set up the function. And then I type in z of that number, and it gives me another number. And since they're virtually the same, I could try it again and see if it changes. If it doesn't change, then I'm done. Copy. So those are identical, right? So I'm done. Once I've done it twice. if I say to do Newton's method, you have to do Newton's method, and this finds that 0 right there to a lot more decimal places. So instead of having 5 decimal places, it has whatever that is, 10. My question to you is this. What if I repeat again and again and again some other number like minus 10? See, minus 10, this is what's called the guess. This is the initial guess. It's minus 10 and it gave us the same answers that everything else. But if I try a different answer, like if I try an initial guess like 0, do it again and again, I get a different answer. I get this answer right here. Okay. And if I try the number 2, I get the other answer, 1.87. That's this one. So this one has 3 zeros. And depending on what my guess is, I may or may not get, I may get one of the 0, the other 0. Okay, any questions on Newton's method before I let it go? Move on to higher order derivatives. Okay, so if you take the derivative twice, that's called the second derivative. If you take it 3 times, it's the third derivative. If you take it 4 times, it's the fourth derivative. Okay, we can write it in function notation. We can also use primes. F prime, 1 prime is the first derivative, 2 primes is the second derivative. I don't think Desmos supports the 3 primes. Okay, so in other words, if I say something like g of x equals, I don't know, x to the 5th power. Okay, I can ask for g prime of 1. That's the first derivative. I can ask for the second derivative. I can ask for the third derivative. I can ask for the fourth derivative. And then actually, eventually, it goes, well, Desmos didn't used to do all of them. Now it does. Each one of these primes gives me another derivative. That's cool. Okay. Acceleration is derivative of velocity. It's acceleration is derivative of velocity, which is the derivative of the position function, and the second derivative of the position function. All right. Let's try saying some of these. I posted some we can talk about. Where are they? When you guys move your hands in the classroom. Sebastian, could you like wave your hand or something? What am I looking for? Just say it out loud. Okay, here we go. So regular derivatives, you want me to say? I'll put the answers up. Okay, who wants to say this one? I'll start with Slade. Slade, say that one right there, the first one. Make it bigger. Okay. Can you say that?
The second derivative of f with respect to x.
Yes, good. Gar, you. Ruger. I'm sorry. Then Garth. No, you can do this one, Ruger. Go ahead. What's that say?
Third derivative of g with regard to the.
Right. You see, if you put the parentheses around the number 3, it means derivative. Also, sometimes they use Roman numerals. I didn't mention that, but you'll see that in Calc 2 sometimes. Okay. God, what's this?
Fourth derivative of c with respect to x.
It's the fourth derivative of c with respect to x. Okay. I'll leave some.
7th derivative of f with respect to x.
7th derivative of f with respect to x. Okay, good. Hold on, we got more. Are you ready to see them without answers? No. Sebastian, what's this?
The fourth derivative of g with respect to t.
Yes. Okay. Home people, Eric. No, Eric. How'd you say number 46?
The first derivative of 1 with respect to x.
Very good. Pam. How do you say 48?
G double prime of S.
Yes, you could just say double prime, means second derivative. Very good. All right, let's see. Johnny. Can you do?
H triple prime of the quantity 2x plus 1n quantity.
Yep, very good. Luke, how about 52?
The quantity of the seventh derivative of m n quantity cubed.
Right. Now you would think maybe you don't have to quantity that. So that's because that in itself is just the seventh derivative. But if you say the seventh derivative cubed, that might work too. It's just I don't want you to confuse it with other things. And by the way, if I put this in parentheses, that would be the seventh derivative. That would be the third derivative of the seventh derivative, which would be the same as the 10th derivative. If I don't put that in parentheses, it's the third derivative of m to the 7th. Okay? All right. Pavani. How about evaluating ones? We just plug the numbers in. So how would you say that first one?
The fourth derivative of f with respect to x evaluated at x equals 3.
Yeah. Very good. Acacia. 72.
The seventh derivative of f evaluated at 11.
Yes. Does everyone understand? You have to be careful. Let me just show you this on Desmos for a second. If you want the derivative, if you have a function, let me just do a simple function. F of x equals x raised to the 5th power. Okay, if I want to evaluate that, if I want f prime of 1, you notice right away to evaluate that. Okay, it knows, it basically is saying this. It's saying, create a new function, let it be equal to the derivative of x to the 5th. Okay, and then evaluate that. Then evaluate that g of 1, and you get, g of 1, you get 5. Okay, so it knows to first take the derivative and then evaluate it. Can I just show you what happens if I write it wrong? If I write it this way, dtx of what is it? F of 1. Why is that 0? Let me just bring it up here. These say the same thing, but why is one of them 0 and the other one 5? Because when you write it this way, it thinks I'm taking a function, evaluating it at 1. What happens when I plug 1 into x to the 5th? What do I get? What's 1 to the 5th power? 1. What's the derivative of 1? 0. So that's why you get 0. Okay. So you have to be careful. This notation on Desmos is not working out well. Okay. But when you write it, if you use that notation, it generally means I'm taking the derivative first and then evaluating. Okay. All right. Everybody got a chance to talk about how you say derivatives. Here, let's try some of these. Okay. Slade, how do you say this one?
The sinh squared of the quantity to x m quantity.
Yep, very good. All right, here's a hard one. Example 2. Alicia, you want to do this one? Right here.
Hyperbolic cosine of x squared plus hyperbolic cosecant.
Yeah. I don't like that. You know why I don't like it? Could you just tell me what this is? Could you read that one now?
Oh.
Gosh, the hyperbolic cosine.
Oh, I thought you wanted me just to read the x.
No, I want you to read the whole thing again. I just changed the parentheses, but I want you to read it again.
X squared
Uh,
plus
hyperbolic
hyperbolic
cosecant.
cosecant x.
Yes, but you would have to say quantity and then quantity because, well, the reason I said that is because if you, the way you said it the same way both times. Which is what it says here. You read what it said here, but what it says here is not, you have to be careful. These are different things. Okay? So if you say the hyperbolic cosine of x squared plus the hyperbolic cosecant, you might, that's the way I would interpret it, what's said there. But if you say the quantity x squared plus cosecant, then that would be something else. Okay, how about this one right here? E3. Who at home would like to answer that? Aiden. E3. How would you say that?
One over the inverse hyperbolic cotangent of x.
Yeah. That little minus to the minus one, that means thank you. That's what I want. Okay. And the last one, Pavani. What's that say? The example 4 says,
The derivative of hyperbolic secant evaluated at 3.
yeah, that's it. All right, so now you know how to say them. Okay, let me leave that. And let me look at the homework. So how are we going to do the one homework question that has to do with higher order derivatives? How are we going to do that? The fourth derivative. And by the way, that should be in parentheses. I'm sorry, because nobody said anything about it. It's a fourth derivative. How do you find the fourth derivative of this? What's the first derivative of what's g prime of x going to be? You need to practice. What is that going to be? Anyone? Pam? Uh-oh. What's the derivative of 5x to the fourth? What's the derivative of that? Just the 5x. 20x to the third. Thank you. Plus. Who wants to do the next one? Acacia, what's the derivative of 7x squared? Okay, you be next. What's 7x squared? Acacia, are you there?
Yes, I'm here. Sorry,
The derivative of 7x squared.
I'm not sure.
I'm not sure. Rudra, you were raising your hand. What is it? Derivative of 7x squared. 7x squared. Derivative. What's the derivative of 7x squared? Right there. 7x squared. Well, derivative of 5x to the fourth, I brought the 4 down, multiplied the 5, and I had 20. And I subtract the power. 14x, thank you. And the derivative of minus 5? 0. Just 0. Okay, g double prime. How do we find the second derivative? Who's next?
That's 6x squared plus 4.
60x squared. Thank you, Eric. Is there anything more?
Plus 14.
plus 14. Thank you. Okay, Sebastian, you can do the next one. G, triple prime.
It would just be 120x.
That's it. And Luke, fourth derivative.
With just 120. Wait, yeah.
Yep, that's it. Okay, and fifth derivative. Johnny, what's the derivative of 120?
0.
0. And every derivative after that, what's the derivative of 0? 0. So all the higher derivatives after 4 are 0. Okay. Polynomials always run out. If you have a polynomial of degree 3 and you take 4 derivatives or 5 derivatives, that after that it's 0. Okay. What do these things tell you, by the way? I guess I didn't really tell you what the second and third derivatives do. By the way, the third derivative, so the first derivative is your velocity. So if you're moving at a certain speed, that's velocity, right? If I'm moving backwards, then it's negative. So it's forward this way, negative that way. What's the second derivative tell us? That's acceleration. So that tells us how the velocity is changing. So if the velocity, if I'm speeding up, then I'm accelerating. My second derivative is positive. If I'm slowing down, it's negative. What does the third derivative tell you? The third derivative tells you how the second derivative is changing. Is your so acceleration. So if you go from speeding up to slowing down, then you definitely, your second derivative has changed, right? So your third derivative is how much that's changed. But you know what it's called? It's called the jerk. When a person calls you a jerk, has anyone ever called you a jerk? Ever? You know, people call them, you guys, what is this new internet thing? You shame people on the internet, you don't call them jerks anymore? Yeah, it's just, I kind of like the term jerk, and I use it freely. Jerk, my boss is a jerk frequently. Let me tell you why they're a jerk, because I'm being mathematical, I'm not being petty. A jerk is when you move forward, you're accelerating, then you decelerate, and then you're accelerating again. That's a jerking motion. In a car like this, that's a jerking motion. My boss says they're going to do something, and then they back out of it. That's being a jerk. Yes. So they've accelerated, and then they decelerated, and then they accelerated. Very clinical. You know who you are, boss. Watch them watching me all the time. So they have all the time in the world to watch my hours and hours of videos. Okay. Any questions on that? So Slade, do you know what a jerk is? Anyone ever call you a jerk?
Yeah.
Did you ever call anybody a jerk?
Yeah.
I'm sure you're doing it mathematically. The jerk is the third derivative.
Okay.
But acceleration is your second derivative. But if you're talking about acceleration changing, it gives you a jerking motion, and that's a jerk. Person being a jerk. I think of it all the time whenever I say someone's a jerk. I'm like, and if they call me a jerk, I'll be like, hey, I was consistently nasty. That's not being a jerk. A jerk has to be nice and nasty and then nice again. That's what makes them a jerk. So be careful how you use the terminology. Anyway, calculus is a study of change and jerking motion. So honestly, we talk about acceleration because you know what acceleration is. When someone takes a car and go from 0 to 60 in 5 seconds, do you guys do cars at all? Is this another thing that I've lost? I've really lost touch with the world. Maybe it was COVID. Maybe it's just being old. Maybe I was never interested in cars when I was in high school, but everyone was interested in cars in high school. Anyone here interested in cars? Say you look like you might be interested in cars. No.
A little bit, but
No.
more of a, I like trucks, but
Okay. Same thing. Trucks are good. What type of truck do you like?
the GMCs.
Okay. That's not very specific, but it's
But
I remember when I was in school, people talked about cars all the time. And then when I got into college, people talked about computers all the time. like my computer has this RAM or that, like they were really into computers. Mostly college people are kind of nerdy. High school people still like the cars. But I don't know what you guys like now. But I'm just saying, I'm bringing it up because acceleration was important with cars. Third derivative, nobody cared about third derivatives. And it's very possible that no one will ever care about third derivatives, but you might. Your world is getting to the point where third derivatives, I say, if you can get them easy on Desmos, you might actually care. And it's describing a type of change. Second derivative describes an acceleration. When you've been doing your projects and you have a positive value, and say, I said it's accelerating by so much or decelerating, that describes the shape of a curve. The curve is increasing, it's going up. But if it's accelerating and increasing, it's curving like this. I don't know if you can see me at home. It's curving like it's going up, like a parabola goes up. And then if it's increasing, but it's decelerating, it's going up still, but it's bending down a little. And that every time you put a bend in a curve, you're adding a little bit more of the higher order derivative. And that's what you're going to learn in Calc 2. Just adding, it's like adding colors to paint. Like if you want, if you want to have a little more green in it, you put some more green in it. But if you want to have less green in it, you put white in it. And so one's accelerating and one's decelerating. Okay. Let's break up into our groups now. I've talked long enough. So for our group stuff, by the way, I did show you, you get the formula sheet. You have formula sheet that's available on all tests, so that's fine. That's homework. I did put over that. Hold on, I'm just cleaning this up. Okay, so this is more homework. Getting rid of that. All right, so high order derivatives, got rid of that. So now we're doing our group work. So what should be done now is you should have finished the transcendentals. Everyone did everyone do the transcendental sign regression? It looks like everyone did a sign regression. I thought we have 4 groups in this class, don't we? Okay, so one of the groups didn't post anything. Sebastian, who's in your group?
Aiden, Eric, Carlos, Justin.
Somebody comment? Aiden commented. And he wrote, according to sign regression with a period of 16 at month 2, the drug potency is 102 micrograms and drug potency is accelerating by 1.3 micrograms. Drug potency is also accelerating by 0.3 micrograms per month. Okay, that's very nice, Aiden. Very good. Okay, and it matches here. Okay, and you picked the time in between here, so it made sense. You didn't go past this because this doesn't make sense. So we're using a sign regression, but it doesn't make any sense. Because drug values, unless the person's taking drugs or whatever, they keep refreshing the drugs. Okay, now previous post. Alicia. Oh, and look, Alicia did post the link to the Blackboard. Did you post that, Sebastian? Do you have that somewhere? Always post that link.
I sent it to, like in the Zoom meeting, I sent it in the chat.
And they took the copy? Yeah. Right. Alicia, you should have opened this up a bit. You know how to do that?
Sorry.
It's okay, because I don't know what this is, but I know it's a second derivative. Okay, and your period is how much? From 1960 to 2060 is, looks like about 1960 to 2060 is how many years? 100 years? It's probably 120, I'm guessing. Because it's 1960 here, because it's 2080 at the bottom, so that's 120. So your period is 120. Did whomever replied to you say that? No.
Oh, is it 6? but the.
It says 60, but it's wrong because that number, that 2 should be a 4. But if you change it, you'll mess up your, see this function is this pi over C1. If you change that to a 4, you mess this up and then it changes everything. So your best just to ignore that number and say 120. I'm gonna look, when I grade them, I look to see how far, I look at that. I look at the actual period on the graph, okay? What did Luke say? Okay, so Luke, you're gonna fix that? Pavani, what did Pavani say? I just have to see this, sorry. Okay, so I can see the closed captioning and it looks like it's correct. But I can't hear that. Can you hear that? This? I was watching a movie the other day and I had to I didn't have the closed captioning on and somebody spoke gibberish. And I was like, oh, I hate that I'm so old. So I turned the volume up really loud and I stood next to the screen to listen. Like it still sounded like gibberish to me. And so then I put the closed captioning on and the closed captioning actually said speaking gibberish. And I was like, really messing with my old age, man. I can barely hear that because it's so noisy, but it's okay, Pavani. I think it's fine. The closed captioning is fine. And Pamela said the same thing. It looks good. These look good. Did everyone post something here? So you had a speaker, you had a writer, and you had a presenter.
Should we just have
You should change it. The period has to be changed to 120.
change the number in the graph, or do we just ignore it and just rewrite it?
You ignore it and you just write. For you, you could write, you just add here, you could add a comment. Period is 120. Then just leave it. Because that doesn't say the period. That says C1 equals, it does not say period. So you can write period anyway. You have no confusion. Okay. All right, good. Sleeve. What are you guys talking about? Selena, can I play Garb? It's going to be garbled. It's going to be good.
G of 75 equals 2.64 BFF. G prime of 75 equals to negative 0.038 BFF per $1,000. G double prime of 75 equals to 7.441056 times 10 to the power negative 4 BFF per $1,000 per $1,000.
How come Selena's doesn't match yours? According to sign regression with a period of 320. Oh, because she's doing a salary of 20. Anyway, I have objection to this. This is in fact the answer, right? That's 7.4 times 10 to the negative 4. But that's almost 0. That times to the negative 4th is like 10 thousandths. So this is 7 10,000ths. So it's really tiny. So the acceleration is virtually non-existent. And you might get away with just saying approximately 0. You can be more precise. But if you're speaking it, you would not say that number. You would say 0. Decreases. I don't know what this means. So Selena, what did you do? Selena, which one are you doing here? 25? Which one is 25? Where are you getting it from this table? 25. Whose table is this? Is this yours? Who posted this?
That's ours. There are.
Slate, that's you. So you posted this?
Yes.
Where did you get the 25 from? Is it A1 or B1? 'Cause I don't know what A1 and B1 is. B1 would be two friends. B1 would be two friends, and it's decreasing by 0.01 BFFs per $1,000, right? And then it's accelerating. So did it have a period of 320? Was that period 320? Okay. $320,000. Okay, with the period of the salary trend, you have approximately 5 BFFs. Where are you getting that from? I don't, that was 5 BFFs. Who's 5 BFFs is around here? Well, it's about right. Maybe that's it. Maybe A1 is that 5 BFFs? Okay. All right, sorry, I just need it to match up. And it does. Okay. But Selena didn't do Rudra. Selena could easily have said, according to the sine regression with a period of 320 and a salary of $75,000, you have how many BFFs? How many BFFs do you have? Yeah, but your mom's not going to understand 0.64 BFFs, so why don't you just say 2 or 3 friends? Between 2 or 3 friends, okay. And as your salary increases, the amount of BFFs increases. Is it increasing? It's decreasing by a very small amount. So it isn't changing by much. And acceleration, that's even smaller. So you could say it's not accelerating. If this is close to 0, it's not accelerating. You know what that graph looks like? That remember before I was telling you second derivative, if it's positive, it's accelerating, it's sort of curving up. And if it's negative, it's curving down. If it's not doing either, it's basically straight. So if I were to look at this graph at 75,000, it should look relatively straight. So here's 75,000 right here. 75,000 is right about here. You see that? That's a straight line. Doesn't that look relatively straight there? That's a straight line. I just asked. See right here, it wouldn't be a straight line. I mean, it isn't, it's straight here though. This is a lot of straight. But this right here is not a lot of straight. But in these parts, it's not accelerating. I would say in this region here, that whole region, those are not really accelerating at all. It's only really in the other regions, top and bottom, when it's accelerating or decelerating. Okay. All right, these were pretty good. I shouldn't have to go over them next time. So why don't you work on the next ones, the mean value theorem ones, okay? So for the mean value theorem one, who gave me a link? Alicia gave me a link. But Alicia, this is what you're gonna do. This is what I want you to do for mean value theorem. I want you to do this. It's kind of complicated, so pay attention if you can. I want you to go to mean value theorem. Oh, shoot. First of all, turn off the sign because we're not doing sine regressions. Turn that off. Okay. Oops, sine regression off. You can leave the data if you want. But I'm going to mean value theorem, opening it up. Without looking at the graph at all, I don't see anything. I know, I need to know what A1 and B1 are. Alicia, what do these mean? Is it between 1970 and 2010 or something? 1980 and 2010. Okay, so remember that. I'm going to turn that on. And that's, it turned the function on too. I don't want that on there. So do you see this blue line there? That's the average rate of change. Okay, now I'm going to click on this one, and that's going to give me the derivative. Oh my God, I can barely see that. That is so not cool. Let me do this. That number, see how that number is 0.07. I'm going to change my y-axis to go between 0.06 and 0.08. Okay, I did that so that I could see where the green and the blue lines intersect. Do you see where the green and blue lines intersect? Do you? Where is it? About when?
Around somewhere around in the 20, somewhere around here.
Looks like 2000.849. So you need to get that number. And you can write this if you want. F prime of 2008.9. Was it 2008.9? 2008.49. 2008.49. Do you see how close these numbers are to each other? So that tells me that the derivative there is equal to the average rate of change over that interval. I don't know what the interval was. So if you'd like to, you could bring them down. You could take the A1 and B1 from up here and bring them down. Where are they? Where's the A1? Oh, so it's 1980 and 2010. There they are. They're right there. So why don't you just do that 1980 and 2010? You could actually do that. You're going to have to if you're the writer. 1980. 1980. To 10. Okay, so average retention. So once you find that value, I don't want this picture. Get rid of it. Lose it. Gone, gone. Now what I want you to do is go back to what we had. So do it this way. Remember this picture, Alicia? I'm helping you here. Okay. What I need you to do is in mean value theorem, you put in that value 2000. So I'm going to take C1. I'm going to put in 2000.849. Okay. So 2000. So you see there's a tangent line. Do you see there's an orange? If you don't see it, it's this one. Do you see that line there? They have to be parallel. And I don't see them, but I'm sure they are 2000. They're right here. They're 2000. See how parallel they are? They're so parallel I can't even see them, but that's the orange. The purple line is this one right here. And it's very parallel to the orange line. So, Alicia, just see if you can zoom out enough so that I can see both of them. Okay, so that's what you want to do.
So what are we including on screenshot?
This much is included in the screenshot. So the writer is going to write something like this. And what is that? Billions of people per year? Okay, so that's what the writer writes. Okay, that's the writer. The speaker is going to say, according to the quartic regression, the average rate of change between 1980 and 2010 is equal to the instantaneous rate of change at 2000.849. And actually, your mom doesn't understand 2000.849, so maybe give it a time. Like, hold on. 0.849 times 360 is, let's see, 65 is 309. 309? What is the 309th day of the year? November 5th. So you would say that November 5th of 2000, the population is growing at that date, at that instant, the same as the average rate of change between 1980 and 2010. Okay, so if you were living there in the hospital and you saw babies popping out or whatever, you'd be like, this is the way it is on average for this whole time between 1980 and 2010. That was a good year, or that good day, November 5th. Before and after, different, but on that exact day, November 5th, babies were popping out at exactly the same rate as they were on average for that whole time period. Okay? And by the way, it's not just babies, it's people dying too. So you're in the hospital, you see babies popping out and people dying, and that rate that's happening then is the same as it is on average for the whole time. Okay? And you only have that one day, and this is just a weird picture, so see if you can get it in there, but yeah. Okay, so I want this picture, if you can give it to me. And I want this, whatever you had done calculations here. I need to be able to see that the average rate of change is equal to the derivative at that point, so when I get rid of this, see, I need to see that those numbers are the same. That's what I check when I grade them. I'm like, if I see a derivative at some point and it's equal to the average rate of change, then you're good. And I also check to make sure that that year 2008 or 2000 has to be between 1960 or 1980 and 2010. And it is. Okay, let's get into our groups. How many groups do we have? 4 groups. Some group is missing, but I don't know who that is. We have 4 rooms here, yes. Do you remember what room you were in the last time? I don't think I have that information here anymore. Okay, the rooms are open. If you remember what room you're in, go into it. Okay, and then I'm gonna look up those rooms. Where were they? They were in. Lessons 3. Okay, Slade, you're in room 1. Acacia, you're in room 2. Acacia, move into room 2. Move into room 2. Cody is not here. He would be in room 2. Eric is in room 3. Aiden is in room 3. Selena's in room 1. Slade, you're on? Is Selena there? Are you in the rooms?
Yeah.
Okay. Garv is in room 1. Garv. That could be in room 1. Sit up closer to him.
Yeah, okay.
Okay. Rudra's in room 3. Rudra, you're in a different room than Garv? Oh, well, not according to my records. She's in room 3 with Aiden. It's okay. Sebastian is here in room 3. Jonathan's in room 4. Where is Jonathan? Jonathan, you're supposed to be in room 4, not in room 2. Wait, I think you're wrong. Whatever, just join your room. Safa is not in any of those rooms. Okay, are you good, Sebastian?
Yeah.
So you guys are moving on to mean value theorem, right?
Can you post the harmonize?
I can. And I will. Mod 4 isn't open either, right? So let me just open up Mod 4. All right, Mod 4 is open. It's Mod 5. Alicia, are you on the line on internet with your classmates? Who's with you? Is Pam there with you? Luke and Pavani? Oh, they're all online. You're the only one here.
Yeah.
That's like,
I'm confused on how to find the derivative.
turn it on. So go to mean value theorem. Are you at mean value theorem? You open
Yeah.
it up. All you have to do is turn on. It should say y equals arbitrary change.
Yeah,
Just turn it on. All right, hold on. Hit the little circle next to it.
yeah, I've heard of them.
Got it? And then hit the little circle for the next one down the derivative. And then look to see where they intersect. You're looking for the intersection of the green line and the blue
They
line.
intersect at 2 points.
Then you need both of them.
Okay,
And they're both within your, what's your A1, B1?
75 and 100.
And those two that you find the intersections are between.
It's actually only one is in between it, so only put the one.
They only did the one. Don't give me the other if it's not between 75 and 100. How you doing, Sebastian? Okay?
Yeah, I just don't figure out how to change it to exponential form.
What? Oh. What do you mean exponential?
Because we changed our original.
You can leave that.
I can just leave it and put it for question.
I mean, either way, I don't care. You could use this mean value theorem will work for the exponential regression as well as it will work for any of the other regressions. But you might have to change whatever it says. If these f's are not the function that you're using, then you'll have to change them. But yes, you can, whatever function you're using, just use that notation. If it's P3 or E or F, whatever, use that. Johnny and Acacia are the ones that are. I'm joining that room. It'll take a minute though before that happens. Content of this meeting is being sent to YouTube. Cool. Okay, cool. Okay. Think we're back. I'm just going to peruse the quiz for you. All right. Quiz question number 1. So this is on mod 4, right? So mod 4 is due next class. So the first question is, what does Newton's method do?
Excuse me, but you are not sharing it on the class.
Thank you, Eric. Thank you, thank you, thank you. When I go into a breakout room, it stops sharing. And I appreciate you telling me that. So can you see it now? I just wanted to quiz. I'm looking at the quiz you have to do that's due next Tuesday, along with the discussion that we already went over. What is Newton's method good? What does it do? Which of these does it do? Is it the second derivative? Is it the derivative of the outside, leave the inside alone, multiplied by the derivative of the inside? This sounds like, okay. The derivative of the outside times the derivative of the inside, what does that sound like?
Chain rule.
It's a chain rule, derivative of the chain rule. Okay. Sinh and cosh, probably this is like, what's the derivative of sinh? And the other one's probably what's the derivative of cosh. Okay. Implicit differentiation you use when you have an equation. The second derivative is another word for what? Acceleration. That's right. Yeah, it is. The second derivative is acceleration. You're right. What did you want to say? That's A. Begins with A. You had it. Okay, so none of those are Newton's method. Newton's method is used to find the zeros of an equation. Okay. So there you go. Now we know what all the questions are that they could ask. All right, say this. So this is the derivative of what? What's that mean there? What's the TANH? What's that mean? Hyperbolic. So this one says the derivative of hyperbolic tangent is the hyperbolic secant squared plus the fourth derivative of g evaluated at 0. Is that it? That's it. Okay. But by the way, you could see there were other ones. Those other ones are the other questions you might get asked from this quiz. All right, here's a bunch of stuff. What lines were we supposed to look at? 17 and 18. But you could look at all of them if you want. What's happening here at 17 and 18? What they do. And don't, again, you have lots of choices. There could be power rules in here. There could be quotient rules in here, or power rules and product rules. I see a product, I see a power. But what is happening here is there's no product rule happening, and there is no power rule happening. All I did was take the derivative of each side. So what is that when you take the derivative of each side called? Which of the, was it, it wasn't a product rule. It wasn't Newton's method. That's finding zeros. It wasn't, right. It wasn't power rule and chain rule. It wasn't the position acceleration, because that would have had an S in it or something. It wasn't the fourth derivative or the derivative 4 times. It was implicit. That's all that was done there, nothing else. So on the test, it might give you lots of answers, but you have to pick the only one that works. Okay. Use Newton's method. Okay, so I think I can copy this and go into my Desmos formula sheet. But when I paste it, it's going to drop that 3. So I have to raise the 3 up. Okay, so that's my function. F of x equals that. And then I graph it, and look, there's the 0 that I'm looking for. I'm looking for that 0 right there, 2.0, that one. So I'm going to copy that. And then let's put it here. All right. That I need to do this. That's the formula that I want for Newton's method. So I'll just create a z of x equals that. Okay. And then I'm just going to take z of this thing right here. And I have, so can you remember 14.8.1? You know, I don't need to remember it. I'll just copy and paste it. So this was the answer that I got. Now I'm going to do z again. And this is the answer that I got. Have these changed at all? Nope. So I have the answer right here. I only need 6 decimal places, so I need that. Minus 2.09455 something. Oh, I only need 6 decimal places. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And the rest won't do. Okay. And then sunflowers. Okay. To determine the sunflowers, this is the worksheet. We want determine the period and in the 43rd week. So to determine the period, so what's the period of this? Is it 10? Does it look like it's 10? It's not 10. I go from the bottom here, which is close to -1, to the bottom here, which is 20, or 19, so it's 20. So it's twice that number. So the period is 20, and then we needed to know it when it happened. The period is 20. And we want to know how big they are at week 43. So just go in here and type in 43. So they want whole numbers, so that's 67, 31, and 3. 67, 31, and 3. And then it says, make sure you use the units. So what are the units? It's 67 cm. And then it's cm per week. And then it's cm per week per week. Okay, let's see if that's right. It's very possible that that's wrong. Let's hope it isn't. Got it, got it, got it, got it, got it. Ooh, it wasn't wrong. Any questions on that? So those were perfectly good examples. This one wasn't. Question 5 is pretty easy, right? Question 5, when you're doing a Desmos thing, it's kind of easy. Question 4, Newton's method. Okay.
That's probably the hardest one.
That was the hardest one. 4 is always the hardest one, but you can look that up in the homework if you want to know what to do. But also, 4 is this is Newton's method. If you take the quiz again, it'll be something else. Maybe you won't get Newton's method. Okay. All right, I think that's it. Any other questions before I let you go? Good. Everyone good? People at home, are you good? I'll be done. I'll hang around a little bit till my live stream ends at 7:50, which is 2 minutes. Everyone else can go.
Thank you.
Have a good weekend. I'll see you next week.
See you next week.
See you next week.
Take care.
Have a good weekend.
You too. Slade left, but he's still on. I'm gonna kick him off. No, I'm not gonna kick him off. Acacia, do you have any questions? Because I'm shutting it down. Everyone here is gone. Are we good? Are we good?